Okay, hello class. So today's homework video is going to be a pretty quick one because you only have 5 problems. Okay, so problem 1. On the surface of the moon, an astronaut has a weight of however many newtons. The radius of the moon is this constant, gravitational constant is what it is, and the mass of the moon is also a constant. So we have to calculate the mass of the astronaut. So realistically, all we have to do is just go G, mass, moon, mass, astronaut, and this is all over r squared of the moon because they're on the surface of the moon. So very quickly, you just have to solve for the mass of the astronaut here. So you just have to rearrange this algebraic equation for MA. So next up, the radius of the Earth is equal to its radius, and the acceleration of the gravity at surface is equal to g. Calculate the altitude above the surface of the Earth in meters in which the acceleration due to gravity is g is equal to whatever they give you. So we get immediately that that g naught here is going to be equal to g me over re squared. And so in order to get the account for the extra altitude, we just have to go that g is going to be equal to g me plus the extra radius. So it's going to be re plus that altitude a squared. And so what we do is we have to take these two equations and we have to divide each equation by each other to get the value of h here. And so we get that g naught over g is going to be equal to, these get canceled out, and then we have that we have 1 over re squared at the bottom, and you have re plus a squared here. And you go ahead and you solve for a. And so all you have to do here is you take re squared to the other side, take the square root, add, and then add re. And then you can go ahead and simplify that or plug it in there. Problem 3. A planet has a mass of 3m and radius r, while planet B has a mass of 4m and a radius of 2r. So all we have to do here for this, okay, so enter expression for the magnitude of acceleration of the rock immediately after it is released in terms of mr and a gravitational constant g. Okay, so there's a rock released halfway between the planet's centers at point O. It is released from rest. Ignore any motion of the planets. Okay, so let's just draw this out actually. So this has radius r, mass of 3m. This has a radius of 2r and a mass of 4m. Okay. And they're separated by a distance of 8r, and there's an object halfway in between them. So this is going to be 4r and this is where our object is going to be located, in the middle of these two. Okay, so enter expression expression for the magnitude of the acceleration of the rock immediately after it is released in terms of mr and g. Okay, so we just have to, in this case, sum up the forces. So sigma f is going to be equal to negative g for the first planet, and then we're going to go 3m, and then the mass of the rock m, little m, and then this is going to be 4r squared, because that's the distance between the rock and the planet here. And then on this side, since this is going to be on the other side, we say that this is negative minus g, and then we have 4m m over 4r squared. and remember that all of this is equal to little ma. So it's asking for the acceleration. So one thing we can immediately do is get rid of all the m's. Makes the problem a little bit easier. And so then this is what a is going to be equal to. But since we have common terms between each of the two planets, we can go ahead and simplify this down to a very, very easy expression. Okay, so first things first is we're going to have a 16r squared on the bottom here. So that's going to be a common factor between the two. And then we just have to, we have negative 3gm over here plus 4gm over here. So then you just combine like terms and you get that this is going to be equal to gm over 16r squared. And so just remember that since we're taking this as our origin point, that the one on the left side here is going to be negative and the one on the right side here is going to be positive. So just keep that in mind. So you have to make sure not your symbols, but your signs align at the correct places in order to get this answer here. Okay, so then it gives you what your constants should be for m and r, and then so you can plug those into this equation here, and then it asks you towards which planet is the rock acceleration directed towards. And this question is a very, very easy question. Since they're both located at the same distance away from each other, then it's just going to be whichever planet is going to be more massive. Even though the smaller planet is going to pull on it a little bit, it's going to pull on it a little bit less. Okay, so problem 4, 2 planets are rotating around a star in elliptical orbits. The orbit of planet 1 has a semi-major axis of A1 in astronomical units, and the other planet has, or orbit 2 has a semi-major axis of A2, which is whatever astronomical units, whatever your randomized variable is. So express the period of planet 2, T2, in terms of T1, A1, and A2. Okay, so for this problem, we're going to have to use Kepler's third law. And so just first thing we have to remember is we have to remember that our centripetal force Fc is going to be equal to mv squared over r, little r. And this is then going to be equal to gmm over r squared. And so then our speed of our planet, once we solve these equations here, is going to be v is equal to gm over r. And this is just done by isolating v in this equation here and solving for it. So this r comes to the other side, cancels with the square here. So you have just an r on the bottom here, and the two little m's cancel. And so then you're going to have g big M over r, and then you have to take the square root, and that's how we get this. And then we just have to remember that the speed is also related to the circumference of the orbit and the orbital period. So then this is going to be equal to 2 pi, and then we're going to have r over t, which is going to be our periods. So in this case, now we can solve for what t is going to be. And so then we get that t, we're going to take t to the other side, and then this entire product over here to this side. So then we're going to have 2 pi r over here, and then we're going to divide by the square root of g m over r, which then we can simplify this a little bit more, and we can say that this is 2 pi, and then this is going to be 3/2 r over the square root of g m. And so we've just taken the square root of r to the top and multiplied it by our r, which is technically has a exponent or an exponent of 2 over 2. So you add the 2 over, you have 2 over 2 plus 1 over 2. And so then that'll give you 3 over 2. And that's where the 3/2 comes from here. Okay. And then we got to remember that for these two planets, then the mass of the star is going to be the same, so the period is going to be proportional to R R3. This is basically what we've just gone ahead and derived. And so then we have that T2 over T1 is going to be equal to A2 3/2 over A1 3/2, which then yields that, then gives us that T2 is going to be equal to T1 A2 over A1 to the 3/2. Okay, so from here, what we can do is we can go ahead and calculate what T2 is, because we are given what T1 is and what the semi-major axes are as well. And then you just go ahead and you plug the numbers in. Okay, so next up we have for our final problem, we have a spaceship of mass m is in a circular orbit around the surface of Earth, or it's some radius above. It needs to be moved higher into a circular orbit of a higher orbit to link up with a space station at that altitude. In this problem, we can take the mass of Earth to be its constant value. How much work in joules do the spaceship's engine have to perform a move to the higher orbit? Ignore any change of mass due to fuel consumption. Okay, so in this case, we have to take the difference in the altitudes as what we're going to be basically what we're going to be integrating over. And so what we can do here is we can say, all right, well, the potential energy here is going to be equal to, or this is going to be 1. We're going to be doing this calculation from potential energy 1 to 2. So potential energy 1 is going to be equal to G M M over R plus H squared, or H is H1, and U2 is going to be equal to G M M over R plus H2 squared. So all we have to do is we have to find this work, which is going to be equal to the difference between these two. So you just have to take U2 minus, or U2 minus U1, and that will give you G M M times 1 over R plus H2 squared plus 1 over R plus H1 squared. And since we know, yeah, that makes sense. We know what the radius of the Earth is going to be. You can just look that up. But if you really want to, we can go ahead and try to cancel these R's out. That'll be a little difficult, it seems. Yes, you just have to get here and go ahead and plug these numbers in from here. I don't think that this can be simplified anymore. So this is going to be a pretty quick video, and I will put this up now, guys. All right, have a good day.